And we have second lecture that is about Boolean model of information retrieval. So in the first, we just mapped the space, was the modalities and applications of retrieval information on web. And today we focus on the first and simplest model of retrieving information for, as full text search. I will first motivate to the whole problem of information retrieval. Also, we'll discuss a bit about the quality of retrieval, how to measure the so-called effectiveness of retrieval. Then I will proceed to the classic Boolean model, and also we'll continue with extended Boolean model that solves some problems that the classic one, the simple one, cannot work with. Okay, so the whole course is about retrieval on the web, but for this preliminary 2 lectures, we will simplify the problem as searching in collections of texts, of plain texts. So instead of HTML documents, we will just parse them, or we'll directly consider plain text documents that are stored somewhere, and that only contain the full text, the text itself. So there is no markup, there are no hyperlinks, there are no embedded multimedia, nothing. We have now the very simple text data type. I haven't introduced the problematics of information retrieval. In information retrieval, we solve the problem of retrieving information on all kind of unstructured data, where unstructured data is a type of is a data entity that has no internal semantic structure, and therefore the search in this kind of data is inherently not precise and must be realized in some approximate way. So the modeling of the data itself will be not exact. So this will be very different from, for example, relational databases, where in relational database we have exact information, we have exact language for querying, and we have exact answers. The results in the answer completely fulfill the query. Here in information retrieval, no matter of what data type, multimedia, text, whatever, we don't have this luxury property of having exactly described data. So we must simplify the problem. And this is also the reason why we must measure, or we need to deal with the effectiveness, as I mentioned. So we want to achieve as exact search as possible, but from the beginning, the problem is not exactly defined. So the question is how we will search the full texts. Of course, you can use some of the string matching algorithms. For example, you know from the algorithm class that there are many of them. The most famous one are listed here: Knuth, Morris, Pratt, for example, Haug-Korasik. And you can take the whole collection of text documents as a one large full text document and just search the occurrences of strings, which are the queries. But this is completely not the solution. Not only because this is extremely slow, because the whole collection must be searched, and the complexity of all of these algorithms is super linear. And but even if it would not be slow, it would be very limited in the retrieval possibilities and in the expressiveness of the search itself, because everybody uses Google, right? So we are not we are not searching for exact occurrences of some substring, but we search based on keywords, and we even do not require exact form of the keywords that we enter as a query. So we must come with some different model that basically will satisfy the user needs, and the user needs are retrieval of information that is related to the query, but is not completely exactly matching the query as in its verbatim form. So that's why we do not rely on any algorithms for string processing or string search. We will create a model that extracts some simplified information from the full text, basically represents the text as sets of keywords, and then we will use this set-based model to answer the query. And today we will talk about Boolean model, which address the problem using the Boolean formulas, Boolean queries. And next time we will proceed with vector models that are more versatile and are used nowadays and are basically really the right models for searching. And there are also probabilistic models that solve the problem as a probabilistic problem. So instead of measuring true or false, that will be today. If document is relevant to query, that is similar to the relational model, or if the relevance is modeled in terms of geometric distance, which is the case of vector model. In probabilistic model, the relevance is addressed by the concept of probability that the document is right or not. So there are three different classes of models, but the practical ones are the first two, and basically the most used is basically the class of vector models. But for simplicity, we also introduce the Boolean model because it shows us the very basics of information retrieval that we will also use in the other models and in the further discussion. So before we stick to the Boolean model, let's have some basic definitions. So we have just full text and a collection of these full texts. One of the entity will be called document. So we'll have one document is one of the database object that is of our concern, and it could be just document as a Word file or something, but it could be really a piece of text, no matter if it's stored in some file or it's just annotation to something else. It's just a meaningful piece of text that has the structure of textual document. So there is some natural language, and the text is not trivial like two keywords. It could be, of course, trivial as 2-3 keywords, but mostly we consider longer text from a small article or a small paragraph through I don't know, 2-page article in newspapers till the very long documents as books and so on. So this is document. A set of documents will be called collection. So collection is set of your key documents. Term is basically word appearing in the document, but term is not every word. Also sometimes called index term. And the terms will be created from the words in the collection, but mostly there will be much smaller number of terms than the words that appear in the document, because the words will be collapsed to terms in order to capture the same meaning by one term, and ignoring the morphology, for example, of word, past tense, and so on. And then if we just gather all the terms together, we get a vocabulary. So this will be the set of all distinct terms over the all collection of the text. So these are 4 terms that are crucial to further discussion. We have also example here to just imagine the scales and the numbers. Let's have 1,000 newspaper articles just imagine how typical article looks like. Each article could, for example, contain 1000 words. That's not that big article, but not that small. But in this 1000 word, there is maybe only 50 distinct terms. I will show how these terms are constructed. And we can also assume that the whole vocabulary, when taking these 1000 articles, and there is 50 terms per article, they could have, for example, 10,000 distinct terms, right? So these are the typical numbers for this size collection of text. If we take larger collection, for example, 10,000, 100,000 newspaper articles, we could get vocabulary, for example, 100,000 distinct terms, and this is the scale of vocabulary for natural language. So there is a maximum. We cannot get much higher number than is the number of words in natural language. So the collection is could scale to millions of articles. The length of the documents also can scale to many thousand words, but the vocabulary is probably limited because of the language that is used. Of course, if we have some artificial language that is not limited, we could also have vocabulary that also grows in unlimited size, but it will not be a typical case. Okay, now we need to pre-process the collection. We have the 1000 of documents. If we do not pre-process the full text, we get all of the words that appear there, but because we will not analyze the text on some linguistic basis, we only will represent the documents by the terms they include, but independently. There will be not represented in sentences, phrases. They will be there just as a set of terms. Therefore, we don't need to keep words that don't carry meaning by themselves. So, for example, the modal verbs and very frequent prepositions, for example, and these types of words that appear and work as a glue for the sense-carrying words, they are not needed here, because if they are represented individually only as terms, not as connectors of two words, then they do not have any meaning there. They only represent digital noise in the collection. So therefore, these words are called stop words, and the definition of stop word is easy. It's a very frequent word, and if the word is so much frequent that it appears in almost every document, then it cannot distinguish between the documents, and therefore any query that contains this word would return all of the document. So that's why these words are not discriminative and not useful for querying, and they are called stop words and are filtered out even in the pre-processing step of retrieval. So we get rid of all of these words. Then we need to simplify the remaining terms, because we end up with words that are not stop words, but these words are present in many forms because of the linguistic modifications of the same stem of word. So we need to make the search more robust and make the vocabulary more compact. And for both of these steps, the lemmatization or stemming simply is processing that is desirable. So, for example, 4 forms of the verb go will be simplified to just one. And from now on, it will not be basically represented as a word, but it will be just identifier of a token, of a term. So the term has some ID, and will represent all of these terms that map to this term, these words that map to this term. Okay, once we do these two steps, we get small vocabulary, let's say 20% of the original vocabulary, which leads to more compact storage, faster search, but also to more effective search, because this is the problem of quantization. In quantization in information retrieval is a very crucial task, not just in text retrieval, but also mostly in multimedia retrieval, but also in text retrieval. What's happening here is basically quantization. We map many occurrences of the same with slight changes to one. So there is quantum like this, and we have multiple variants. And if we use quantization in search, we are able to match different words on each other if they belong to the same quantum. So this is how we can effectively search by the verb go, even terms that were not sharing the characters, and it will be, for example, as went in the other document. So this quantization effect is leads to more effective search. When we will discuss more about the quality about the effectiveness of the retrieval, we must ask question how to measure the user satisfaction with the result. This is the problem of effectiveness. This is not a problem, as I said, for example, in relational databases, because the user has full control on the retrieval process. The user has the SQL select query and exact formulation of the query. So what the user specifies, he gets, and it's true-false problem. But in information retrieval, the user basically does not have very precise tools for formulating a query. We have here, given the model that we introduced right now, we have the terms, and we can ask whether the terms are present in the document or not, or how they are present, if they must be together or cannot be together, and so on. And based on this, we will evaluate if the system returns relevant results or not. In terms of measuring the effectiveness, we need to have some benchmark collection or benchmark that includes the queries and relevant documents to the queries. So the concept of relevant documents, this is something added externally as a external annotation of a so-called ground truth collection that is labeled as a relevant document to a particular query. If we do have this benchmark, this ground truth, we can evaluate how good a certain system is or is not. So yeah, this is the way how we can measure the effectiveness. Of course, the ground truth, the annotated collection that we use, must be representative in order to be satisfied this assumption, that is extrapolation assumption, that the system will be evaluated on some benchmark collection, but should work the same or very similarly on other collections that are not annotated, and therefore we don't know we cannot evaluate effectiveness on these collections because we don't have annotations for this collection. So that therefore we need a ground truth that is representative and can be extrapolated to other types of collections. This is of course a critical assumption. And when measuring the effectiveness, we have very basic measures for measuring the effectiveness, and these are precision and recall, where the precision measures the probability that a document that we like as users is actually in the answer, in the query result. And recall is a complementary. That's probability that the relevant document that we would like to obtain actually appeared in the result. So this is depicted by these two sets. So we have a system. The largest ellipse is the whole collection. There is some query given, and the engine returns this set of results, the blue one. And this is what actually the system returns. But the system, the perfect system, should retrieve the green set of results, and this is the annotated set of documents that should be returned to the given query that we are now solving. And the better system, the more similar or more overlapping these two sets will be. And the precision and recall will be computed as the proportion of this overlap, either to the size of the set that was retrieved, or to the size of the result that should be retrieved, right? So in this particular example, in this figure, we can see that the precision will be something like 20%, because 20% is basically the portion of the blue set that is at the same moment also green. So this is maybe 20% of the blue. From the other side, this is maybe 1/3 of the green. So the recall, the probability that a relevant document is also in the result is 1/3. We can also define these two measures very intuitively as a task. If you randomly pick one of the documents that were actually returned, what is the probability it will be in this location that is also green? Okay, and it's by 20%. If I randomly just pick one point here, in 20% cases it will be here. The same for recall. What is the probability that any green relevant document will be also in the blue set? And again, it will be maybe 30%. So this is the basic for measuring the effectiveness by precision and recall. If we talk about the instances here or here or here, we use this terminology. If we have returned object or returned document in the query result that is not relevant, so it is not in this overlap but is here somewhere, then this document is called false alarm, because it was retrieved but was not relevant, so was false alarm, this terminology. And the increasing number of these false alarms means this blue portion of the whole set is larger with respect to the overlap, and the precision therefore decreases, because there is many of false alarms and only a small number of relevant objects that were returned in the query result. On the other hand, false dismissals are documents that are in the green set and were not in the overlap. So these should have been retrieved, but were not. And that's why there were false dismissals or false drop. We don't know about them because we didn't retrieve them, but they should be retrieved. Of course, we can measure this if we have the annotated collection, but if we don't have annotations, we cannot know how many there are false dismissals. This is some asymmetry in these two situations, because in false alarm case, we basically can recognize a document was false alarm because the user says that. User can say, okay, I have this answer from the system, and I like these 4. These are relevant for me, and I don't like these 3. And these are false alarms. But if the user retrieves information and it's incomplete, the user doesn't know what was the false dismissal, because the user doesn't see it, right? So it's much harder to identify false dismissals than to identify false alarms. And such as false alarms where decreasing relative precisions, false dismissals decrease the relative recall. When speaking about precision and recall, there is use a standard model for showing the behavior of the system when the precision is dependent on recall, and it's called precision recall curve. It must be said that the precision of search cannot be simply controlled. That's the hard problem, but we can simply control the recall, because what is recall? Recall is the proportion of this to the whole green, to the size of the green, and we can deterministically increase the recall just by a naive algorithm of expanding the query result up to the size of the whole collection, right? So once we are increasing the radius of this ellipse more and more and more, at one moment we basically cover the whole green set of relevant documents. So this is the way that we can iteratively increase recall. So we can really get, every time we can get 100% recall, but for the price of typically lowering the precision.
So how do we know that the document is relevant? We recreate.
Yeah, this is only in the so-called training phase, right? So if we measure the effectiveness of a system, we have so-called ground truth, which is a collection with annotations, and annotation means that's the assignment of a document, whether it's relevant or not.
So this is only in training. We know in advance which are.
This is like training collection. It's not training, because in information training is a terminology for machine learning, right? Or something like this that we can train. In this, we only evaluate the system. We do not train the system. We only validate if the system is good or bad by using this annotation collection. But as you say, right, this is only for validation purposes. So in the production search, we don't know this information. That's why we have the training process or the validation process to validate it on some control annotated data set. And then we only hope, because of this extrapolation assumption, that this measured quality of search will also be the same or similar when applied to another collection that is not annotated, because all of the collections, the rest of all collections are not annotated, right? So this is just the offline phase for training, for validation. What we get using the precision recall curve is this basically function. As I said, you can always control this the percentage of the recall by just expanding the result set. Just iteratively, you can imagine, for example, you have Google. You put a query into Google, and you have ranking, let's say 1,000 of pages that are returned by Google, and you can go in the ranking and observe how many of how large is the recall. So let's assume this is something that Google returned, right? And you can expand. This is the first 10 documents, right, that Google returned. If you want to increase the recall, you must take larger. You must take another, for example, 10 documents, the next page the Google provides, and it will expand something like this. and even more, even 10 more, and it will expand like this. And this way you can virtually get the whole collection at the end. But fortunately, hopefully, you will get the 100% recall much sooner than you are forced to retrieve the whole collection, of course. But you are doing this exactly like that. So you are expanding the result until you reach 10% of recall, and you measure for this 10% of recall the precision, right? So for this expanded query, you measure precision. Then you continue, expand until you have 20% of relevant documents, 20% recall, and again measure precision of the whole you have, and so on. And this is how the precision decreases when increasing recall. So this is the typical shape of the curve. If you don't need very good recall, you are probably have the most relevant documents at the beginning of the ranking, and so the precision will be high. The more you get data in order to inflate the query result to achieve higher recall, the less precise the result will be, because it will be more and more noisy and more false hits, and the proportion will go down. So this is precision recall curve, but just we must take in my mind that in our minds that this is just for one query. This is quite complex curve, but still it's only related to one single query. So for some other query, the situation could be different, and therefore this is hard to work with. It's a curve, and not only it's not one number. There are 11 of them, because we have 11 standard levels of recall, 1 to 0 to 1, and 9 levels. So this is 9. So this is 11 precisions, and this is just one query. So therefore, we use more aggregated measures for comparing systems, and the most used measure is so-called mean average precision. I will note, basically, mean average precision means that you compute these precision recall curves for many queries. For this precision recall curve, you compute mean or average precision, which is just averaging these numbers. So you get, for example, 0.4, and take the average of all of these averaged numbers. So this double average, right? So you average every single curve like that, and then you take average for the many queries, and you get mean average precision. Okay, and then you have some more robust and universal comparison of two systems, how they are effective in search. Okay, and now this was measuring effectiveness that is not connected to any particular model of information retrieval. This is useful for any model, but we start today with the Boolean model, and of course the evaluation of searching in Boolean model could be used for the effectiveness measuring. And the same, we can evaluate any vector model or any other model that leads to retrieval of data, right? So this was pretty independent. Okay, so Boolean model. In Boolean model, we have a simple representation of documents based on set theory, and for queries, we use the Boolean algebra. It's the simplest model you can imagine, basically, because document is represented by the set of terms it contains, right? But instead of thinking documents as sets, we will simplify it, and we will represent document as a binary vector, where the dimension of the vector is the number of terms in the vocabulary. So every term has a bit in this binary vector, and this bit is true or 1 if the term is appearing in the document, or it's 0 if it doesn't appear. So we have binary vector for every document, and every term in this vector has its own position, and it's either true or false if it's in the document or not, right? So this is the view of a document, or document-centric view. But because we will ask not using documents but using terms, into Google you type keywords, right? It will be more practical to not represent documents by document vectors, by binary vectors. It will be practical to represent terms as binary vectors, where the dimensionality will be the number of documents. So it's basically the inverse situation. Instead of representing a document and all of the terms have their own bits, we will have term and all of the documents will have their own bit, right? So it's inverse situation. We have term and associated set of documents where the term appears in, and therefore we can have binary vector for every term. But the dimensionality, of course, will be different. There is m terms in the collection if we just do document vector, but there is n dimensions in the term vector, because n is the number of documents. So this is number of terms, this is number of documents. What we get this way or the other way is so-called term by document metrics, where we have already the inverse situation, where the rows in this matrix are term vectors and columns are the document vectors, right? So it's n times m matrix, and if you look orthogonally, or if you inverse the matrix, then you have the inverse representation. So either columns or rows are either document vectors or term vectors. Depends on the convention you choose. Okay, now how this term by document matrix actually looks like. We already have the example with the newspapers articles. What we can say to the statistical properties in such common collections. Probably we will suppose a document in a collection is not very long. Let's say it's 1 to 100 text pages. Mostly it will be shorter, right? And if you can imagine, every normal text document probably does not include very large portion of the whole vocabulary of the language, right? So if I write a short article, 200 words, it can mostly be consisting of 200 words, but it will be probably less than that number, right? Because some words will be repeating and so on. So at the end, the document will contain less than 1% of all words in the vocabulary, and therefore the binary vector of the document will be very sparse. There will almost everywhere be zeros, and from some point to some point there will be just 1, but it will be very sparse. Therefore, the whole term by document matrix will be very sparse, almost zeros there, and this is interesting to count with, right? So we have very sparse term by document matrix and very large, and we will demonstrate the Boolean queries on this example. Here you can see the term by document matrix. Of course, this is not that sparse that I just said, because this is a small example, and in small examples we need to have some true occurrences of terms. So that's why we cannot have here just just one true bit and everything 0, because we could not demonstrate any query. So we have more ones than just typical. And we have documents. These documents are Shakespeare's plays, right? So we have 6 documents: Antony and Cleopatra, Julius Caesar, Tempest, Hamlet, Othello, Macbeth. And we have some selected terms. We have 7 terms, right? These 7 terms. And this vector, or this vector, means in Antony and Cleopatra, there appear these terms: 1, 2, 3, 4, 5, 6, because there is 1 on the term, right? We can see it inversely. For term Antony, there are 3 Shakespeare's plays that include this term. So it's Antony and Cleopatra, Julius Caesar, and Macbeth, right? The rest is 0. Okay, so this is the representation of the term by document matrix. And now to the queries. So the Boolean model is called because they are used Boolean expressions over terms, and these are the queries. And the terminals of the the queries are constructed over the terms themselves and Boolean operations and or not. The terms themselves basically stand for a predicate whether a given term appears in the document or not. If it appears, it evaluates to 1. If it's not there, it evaluates to 0. So once Brutus, Caesar, and Calpurnia are evaluated, because every query is matched to every document, and it could be evaluated to every document. Once the 3 terms are evaluated on a certain document, we get the logical values, and we can evaluate the whole expression, right? And we do this for all of the documents, and only the documents that were true for the whole expression, that these documents passed the query and became the query result. So this is the intuitive processing, but we can do it more efficiently. We can convert these logical operations into bit operations, and instead of evaluating the documents one by one, we can do it at once using bit strings, bit vectors, binary vectors. So instead of evaluating for every document this expression, we can represent the terms by term vectors like this. So Brutus is term vector 110100, 110100, right? In the term by document matrix is the same matrix. Caesar is this vector, Calpurnia is this vector, and because these are the documents in the collection, and we can see from these bit strings the presence of the given term in the document, we can accomplish this Boolean query by doing the Boolean operations on the bit strings, but converting them to logical to bit operations. So we will end Brutus and Caesar, and not Calpurnia. So we have these bit operations, and we get this final bit string that is the answer and says, okay, this query is true for 2 documents. The first is Antony and Cleopatra, and the second is Hamlet, right? It's here. This is some proof, of course, not for not Calpurnia, but this is proof for Brutus and Caesar, because there is Brutus and Caesar, and there is not Calpurnia there. But this is not nicely viewed. Okay, so this is Boolean model and how it's how it's evaluated on the bit string basis. Now, how to efficiently implement the bit operations. Of course, we could have the term by document metrics really materialized like that. So we have all of these bit strings like that, stored somewhere on disk or in memory. But we also said that this matrix is very sparse, right? So there is 99% of zeros, and it would be really extremely inefficient to store directly these bit strings full of zeros and then doing these bit operations with almost zeros, almost zero bit strings. That's why we do not use directly the bit strings, but we use so-called inverted index. Inverted index is a compact representation of the sparse matrix based on representing the term vectors, but not as binary vectors, but as a inverted list. And instead of representing ones and zeros on the particular positions that belong to particular documents, we will only store the ID identifiers of documents that actually contain the term. So we will not store IDs of documents that do not contain the term, so of course. So for example, for Brutus, it's not the case here, right? So in this case, the inverted list would be Brutus 1, 2, 3, and it will be 3 entries. But in reality, this will be just 1% of all of these bits, right? And we have, this is some virtual Brutus, different Brutus. We have this for all of the terms in the vocabulary. So it's basically a representation of the term-based document metrics, but you can also view it as a representation both of the occurrence of the term, but it is also basically a vocabulary representation because you have all of the terms stored here. Every term has its own dynamic list. The elements in the list are sorted ascendantly based on the ID, of course, right? So this is sorted. This is something like skip list, right? So you skip 2, 4, and so on. You have representation of the sparse matrix. Now, because we don't have nice bit strings, we cannot do really bit operations when evaluating the query, but we must work with the inverted list. And because we need to implement the bit operations, but on inverted lists, we must implement basically the operation into the inverted list, and it will be done using a sort of merge sort style, traversing the sorted lists. In merge sort, how it's merge sort done? In merge sort, we basically merge two sorted lists or sorted arrays by walking by a cursor in the one and in the second, and aligning the same positions and actually aligning them or inserting one into the other. But this is the second part of merge sort that we will not be using. We only use this merge sort for keeping the cursors here aligned. So once we keep the cursors aligned, we basically have aligned positions of documents with the same number, and therefore we can retrieve the document vector for the terms, right? So if we have, for example, Brutus and Caesar, that must be in the document to be true for the query, we go and evaluate. So if we start with 2, so Brutus is in second, so we didn't process first yet. Okay, so we wait. In the second, in Caesar, we get the first. Okay, so Caesar is true in first document, but because we are already on position 2 in the Brutus, therefore it was 0 for the first document. So therefore this was 0 or false, and true, it's false. It doesn't go to result. Next, so we move from 1 to 2. We are already in 2 here, and we have true here and true here. And because we have true and true, second document goes to the result. Next, 2, 3. We have 3 here, but next 2 and 4, and it is true for 3, but false for 3 here. Next, this 4 is true, but 4 is not true. Next, 5 is true, but 5 is not true. Next, we have 8 and 8. So again, we are in situations that both are true and goes to the result, and then there is no other alignment that will be true together. So this merge sort evaluation of the Boolean query is the way how to bypass the bit operations, but basically using the compacted representation of the term vectors here. Okay, are there any queries to this? Questions? Everything is clear. Okay. There are other questions how to optimize Boolean search because we can have very complex queries. So we will probably optimize the queries using, for example, the associativeness rule, where we can evaluate this query like this or like this. And here is question: what will be if we evaluate the sub expressions and store the intermediate results? Then different associations will generate different intermediate results, and some of the form is better than the other because of lower overhead. So in this case, for example, the B is faster version, because in B we first do the basically intersection of Caesar and Brutus, and the intermediate result is smaller because Caesar has only 3 frequencies here and Brutus has large, but because of the end it will lead to small intermediate result, and then it's compared to Calpurnia, which is faster than taking it this way, because there is many of Brutuses and many of Calpurnia, so the intermediate result could be large, and then it will get small in the last step. Okay, so there are these options for optimization. We can also optimize by using statistics, of course, and it's also quite expensive to use other than the AND operations, because AND operation is always leading to smaller and smaller intermediate results. So we quickly minimize the result. But when using OR operator or even NOT operator, then it's much more difficult, because especially NOT leads to the complement to the set. And if I want to return or all documents that do not contain a particular term, it will maybe be everything. So this is much more difficult to optimize. It's mostly optimized using frequencies that we already have stored here, but otherwise, of course, it's problematic when using NOT. Or is also problematic, but not as much, because this is just union of 2 small sets, but complement to a small set is a large set, so not this problem. Here, I only show that we can implement the inverted list by some specific dedicated index implemented somewhere, or we can reuse traditional technology. For example, we can store inverted index into relational database in 2 tables, right? So we can have 1 table for the vocabulary and one table for the actual lists, for the dynamic lists. So it will start, every term will start in this in this table with a pointer to the lookup table where there are the lists, and everything is serialized to just one very long list that is composed from all of the other lists. Of course, this representation is problematic if the inverted list needs to be dynamic. If you want to insert new data into then this they might be inserted in the middle of the table, and therefore it must be shifted, and it's not so efficient. But otherwise, it's quite good solution. Okay, now just summarization. What are the assumptions for usage of the inverted index? Inverted index is very efficient implementation of Boolean models. So making inverted index from the terms by document metrics, it's very efficient, but there must be some assumptions satisfied. First, we do not have indexed the really frequent terms, because this would lead to really long inverted lists. Really long. So really long means almost the size of the whole collection, and this would disbalance the whole index. But this is solved in the pre-processing phase, where we drop all the stop words. We already discussed this. So at this stage of indexing, we should not have really frequent terms in the index. Next assumption, we should have queries consisting of very few keywords. Few keywords means up to 10, for example, because this is a multiplicative cost factor. The number of queries in a query, keywords in a query, determines the number of inverted lists in the inverted index, right? So the more we have the lists, the slower the search is. We should have the inverted list sorted because of the merge sort traversal. And as I said, if the collection is static, then it's easy to search the inverted list. Otherwise, we need to solve the insertions of new documents that could be really expensive if it's done using this relational database method. But if it's in memory, if it fits the memory, then it's no problem. We have dynamic lists normally using pointers, allocations, and so on. So there is no problem. Okay. So to summarize the Boolean model, there are some pros and cons. The advantages are that it's really easy. It's a simple model. It's also simple logic behind the model, because documents match or mismatch a query that is given by the Boolean expression. And as we saw, it could be really efficiently implemented using the inverted index. But it's also connected to the cons. To just conclude the pros, it is really competitive, or it's a good solution. The Boolean model is a good solution for very specific professions where you need exact searches that are that basically lead to relational query, right? So the whole Boolean expression basically is exact, right? So we have queries that combine true and false with and or not, and this leads to binary search, right? And the user must be really confident when placing this type of queries, because if the query is wrong, it could end up with zero answer, zero result, or a very large result. So this is the risk of Boolean model. But in some use cases, like lawyers, for example, that really search for occurrences of certain keywords, and basically they really precisely know what they are searching for, this might be a solution. But for most of the users, this is a cons. So Boolean model is basically too rough. In the first place, the representation itself is rough, right? We get rid of the natural language. We only extract the number or the frequencies or the occurrences in Boolean model, just occurrences of terms. So the document is simplified to just a set of terms. And in this simplification, there is much lost in translation, basically, because we have just set of terms, and this led to approximate representation by itself. And then the Boolean querying applied on top of this is basically applying precise searching in not precise representation. And this is bad combination, of course, because we need to somehow express our exact query intent using very vague representation. So we only combine different terms together using and or not, and hope we will get results that will be satisfactory. But they are mostly not, and there is the risk of returning small or very large query result, and we cannot do anything without that. With that, because there is no ranking of the return results. If they are all true, or if they were not returned, they were false. But we have no ranking. We don't have better or worse document in the result because they are all true. So we are basically we have no possibility to structure the query result. And if it's too big, we must throw it away and start to search again, because we cannot basically process large query result. Or if the query result is empty set, then we have also a problem. We must reformulate the query. And there is problem how to reformulate a query. There is no good way of user feedback in Boolean model, because in Boolean model you cannot say you cannot just use the way of user feedback that will be in vector model. In vector model, you just can say this and this result is good and this result is bad, and the vector model could be adapted to return more like the positively selected documents and less like the negatively selected documents. But there is no method to do this in Boolean model, because in Boolean model any alteration of the query must lead to reformulation of the Boolean expression, right? So adding more ands or turning and to or this kind of magic, but nothing is consistent with what the user actually wants to do. So there is a problem with Boolean model. And because of these problems, of course, one solution to this problem is to just do not use Boolean model. But there was also another solution, and that was basically fusing the Boolean model and the vector model together, and was called extended Boolean model. So in extended Boolean model, we keep the querying part. So the query is still the Boolean query. So we have still keywords connected with Boolean operations, computer and mouse here. But the representation of the documents will be different, and it will also provide us with the ranking, because the query will not be anymore true or false. The document to a query will not be relevant or not relevant, but there will be introduced multi-value relevance. So it will be more refined, this evaluation of the document to the query. Okay. The extension is based on basically taking weights from the vector model and using it for representation of documents. But because we still have the Boolean expressions for queries, we must somehow combine these two completely different representations, vectors for the documents and Boolean expressions for queries somehow together. And this is basically what the extended Boolean model needs to address. The weighting of documents will be exactly the same as in vector model. And in vector model, we will discuss vector model next time. But we can introduce this part of the vector model, right? Because this will be completely the same. In the extended Boolean model or in vector model, instead of having binary vectors for terms or documents, we will have real vectors. So instead of just one as true, as appearing or not in document, we will have positive weight that will reflect the importance of the term in the document. So 0 will be the same as in Boolean model. 0 means there is no occurrence of the term in the document, but everything else will be a real number. And the numbers are constructed in the vector model, but also in this extended Boolean model using so-called TF-IDF scheme. We will talk about this formula next time, so I will not now explain what it is. But basically, this ensures that the weight of a particular term x, kx, in document j, dj, is some real number, right? And because I will assign to every term and document a number, then I can visualize the space of documents where we have the axis, all of the terms. In this case, of course, it's only two-dimensional. We have only two terms, term kx and term ky. And based on these two terms, the two documents have these positions, because document 1 has these weights. So these are two-dimensional coordinates, right? Is here, and the second one is here. So all of the documents in the term space will be positioned something like this. And of course, imagine it will not be in 2 dimensions, but in 100,000 dimensions. Will be points in 100,000 dimensional cube. And this is the representation, right? So in reality, the space is not 2-dimensional, but m-dimensional, because m is the size of vocabulary. Every term has its own dimension, right? So every document has the number of coordinates of all of the dimensions of the terms. And this is basically the same from vector model. Now, how to use this completely new information with the querying? And this probably is a problem, because when we have a query and document vector, now it's real value document vector, we need to compute the relevancy score of the document vector to the query. But we cannot compute it as we are used to, because we don't have binary vectors and binary operations that were transforming from the logical operations. We now have real numbers. So we need to implement the ands and ors somehow different than they were just using the binary strings, right? And in this particular case, the and or fragments of the expressions are implemented like this. So instead of and, we will measure the penalty from the ideal case. So if there is perfect n of 2 terms, this is one term, this is second term. So if both of the terms that are in the query, right, it's K1 and K2 here, K1, K2, if they both are in the document, it will be coordinate 0, 1, 1. This is the perfect match, because there was weight of the first term as 1 and weight of the second term as also 1. So it basically it was in the document like exactly. Both of the terms there were exactly, and therefore the penalty from this point is 0. So there will be 0 penalty and therefore the relevance would be 1 minus 0. So it will be 1. So the relevancy is computed for ends. For ends, it's computed like this. It's 1 minus, and this is the distance from this point to the actual position of the document, here or here. And if both of the terms are there with high values, it will be smaller penalty, smaller distance that is subtracted from 1 than if it's lower values. So this is geometric computation of something that should mimic the AND operation, right? It's not exact. Of course, in the special case that we have only binary weights, if we have only binary weights and everything is on the edges of the cube, it would be really the normal classic Boolean model, because then it would sit here with 1 occurrence and 1, and there will be 0, 1 minus 0, and the 1 will be true. So this is AND, right? So it works for the special case, but for the other cases, it's just interpretation of AND for real vectors. The second case is OR, and it's the opposite, and it says, okay, it's okay if there is at least one of the terms in the document. It's K1 or K2. So if there is at least one very high weight for one term, then it will be this distance. So this distance from here to here, and this will be 1. The distance will be 1, and the distance will be relevant. So it's not penalty now. It's the real relevance from here to here. It could be even longer, because it could be more than 1. This is the diagonal. If they are both of the words fully, then it will be here. But again, it more or less represents OR. If it's at least one of the term, it's 1 here or 1 here, or more than 1 here. And again, for the special case of having normal vector normal Boolean model, it will again work, because it will work like binary or here and here. Okay. Is everybody okay with this explanation of how these relevances are computed? Okay, nobody asks. Somebody chats something. Yes. Okay. So this is one more. Wouldn't OR be equal only to 1/2 when Vx is true? Yes, yes, you mean that we are dividing here by the t. Yeah, yeah, because we have number of terms here is t. Yes, it's you are right. Yeah. So there is no good. Basically, I think it's okay, because in the special case, when it's larger than 0, it's 1. Just no matter. We can just process it as if it's 0 on 0, and then it's true, and it's the special case. Okay. And because this was just solution for one fragment of this conjunctive form or this disjunctive form, we must generalize it for the general expression. So if we have, for example, this composed form, conjunctive and then disjunctive, we must recursively apply these formulas. So we will evaluate for the nested expression this AND clause, and then applied to the disjunctive, so means using this entire thing in place of this one weight, and we get this plus the second is the third, and divided by 2, because these are two members of this disjunctive form. But recursively, it could really expand if we have nesting in the expression. It will be quite a large formula for this relevance. Okay, we could also extend this extended Boolean model by using other than Euclidean norms, because this is Euclidean norm, right? So you are really computing this distance, Euclidean distance, either from here or from here. But you can use other form than Euclidean distance. They are called P norms or LP distances, but P norms, where the P is not 2, but we have by default here 2, second square root and power of 2. But we can have P roots and powers of P. And in some using different P's, we can get different levels of precision and recall if we evaluate. So we have another more parameter to tune the model actually. So this is the more general form with the P's here and not just 2. If we compare extended Boolean model with the classic Boolean model, it retained the front end, so to say. So we have the same query expressions. So we switch the engine behind, but we keep the interface the same. We have Boolean model queries. So it's still easy for the users and for the professionals and for everybody. And we get some value from this, and this is the rank queries, because we get these irrelevances, which are real valued numbers, and because of these real values, we can rank the result. So the user then can specify how large the answer should be, because there is nicely ordered result, and the size of the prefix that is regarded as an answer could be dynamically changed. So this is good. And because more delicate matching of the expressions, because the ands and or have real valued interpretations, and there is more information on the term weight, because in the term weights there is more information, because we also include frequencies of the terms in the document, which was ignored in normal Boolean model. Then we should have also more effective search over the standard Boolean model in theory. So the quality of retrieval. For cons, it's more computationally expensive, because we have if we use the P powers, P roots, we also need to have maintenance of the intermediate results. So it's quite computationally expensive. And maybe the largest drawback was not removed, and was also in the Boolean model, and that's how to realize the user feedback, and basically how to construct queries when the Boolean operators basically are too strong to work with, right? So that's why in vector model you do not need anything else than terms when querying in Google, right? You only type keywords, no ands, ors, whatever. And this is much more convenient for end users, and that's why the Boolean model is not used in practical usages. Okay, this was it for today.